Hi, I'm Tristan. I work for Intel Nervana. Today I'm going to be talking to you about Intel Nervana Graph. Intel Nervana Graph is a piece of software that I work on, and it's part of our efforts to develop a universal deep learning compiler, and through that identify a core set of abstractions that should describe neural networks and allow them to run efficiently on a wide variety of devices. Nervana Graph is an open source project, so you can go to the GitHub repository under Nervana Systems nGraph, or you can go to our website at nervanasys.com to view the latest documentation. So I just wanted to thank the organizers for inviting me to this conference. It's been great to see a deep learning track added to Strangeloop. So if you're not familiar with deep learning, I'm not going to be going over the mathematics, but the very simple description of deep learning is it's going to be the technology that you're going to see that enables self-driving cars. And other examples would be AlphaGo, a project from DeepMind, basically mastering the game of Go and able to beat the top human players. So deep learning has its name because it basically describes deep neural networks. This is a very computationally intensive task, and the deep structure of these networks allow you to train these systems to represent multiple levels of abstraction and give almost human abilities of performance on things like image recognition. So it's a very computationally intensive task that basically involves training with lots of data. So having a very performant backend is very important. So here are the sort of background questions for those of you who are familiar with deep learning that might have. So how has the code that we've been used to express deep learning neural networks evolved? What have been the core features of APIs that we have seen over the years for deep neural networks? What exactly is the interface between device hardware and software frameworks? And how exactly is deep learning different than other types of numerical software? So it was back in 2008 when I started my PhD when I first touched on deep learning. And it was just a few years earlier that Jeff Hinton released his paper on deep belief networks that sort of caused this resurgence in the interest of deep neural networks. And at the time, I was basically programming in NumPy or C, or very low-level things like CUDA. And this was a real headache because you basically had to manually specify how to do the sorts of algebra and calculus in order to train through forward and back propagation. Then in 2009, researchers from Montreal released Theano. And Theano was very useful to researchers because it introduced this notion of abstract operations and abstract equations using a sort of symbolic notation, and it took away the pain point of writing your own automatic differentiation algorithms. We've seen a lot of other popular frameworks come up, such as Torch, which introduced the idea of modularity. Torch was written in the Lua language, and you can still use that now with PyTorch if you're more of a Python person. Caffe and Caffe2, which were developed at the Berkeley for computational vision, introduced the idea of a core set of operations that would be useful for doing computational vision. And then, of course, in 2015, TensorFlow was released, which really solidified this idea of a computational graph, which we're all probably familiar with now. Other frameworks of note are Nervana's own Neon, which is designed for data science and sort of pushed the bar of GPU kernel performance. There's Amazon's MXNet, which is for training distributed networks. And now we sort of have frameworks on top of frameworks. One of the easiest ways to get started with deep learning is to use a front-end framework such as Keras. So you can download that and literally get started training a recurrent neural network in just a few lines of code. Of course, there's a lot of other frameworks that I haven't mentioned here. We saw deeplearning.scala exploring the functional paradigm. One of my own favorites is the Grenade library for Haskell, which explores dependently typed neural networks. And so we have this huge ecosystem, and as a user, we're basically forced to choose one and learn that. As well as there being a lot of different types of software, new back-end devices are appearing. So a project that I've worked on is the Crest family of deep learning chips from Intel. So this is a GPU accelerator that's going to appear in the future from Intel. And it's been designed from the ground up for doing deep learning. It's very good at achieving high performance in terms of matrix multiply operations, the sort of core operations that you would be using in a deep neural net. And this chip uses a novel data format. We have a paper appearing at NIPS, the NIPS conference this year about this. So I encourage you to keep on the lookout for that. So as a user, this is great. You have a lot of frameworks to choose from. But the problem is that there's a huge amount of engineering effort in order to map these different frameworks onto different devices. The framework author is responsible for writing a backend for many different types of deep learning hardware. And the deep learning hardware designers and the system software programmers are responsible for selecting a few popular frameworks. So this is a good way to limit innovation by basically locking in an ecosystem. So the solution is the Nervana Graph project. So what the Nervana Graph project consists of is a set of intermediate representations to capture the core abstractions for deep learning. And then it has a different set of compiler backends, or what I'll call transformers, which takes this intermediate representation and allows it for execution on the device. And there's a set of front-end connectors that can plug into new frameworks and existing frameworks. And then we have our reference front end, which is based on our existing deep learning framework, Neon. So this is what the picture would look like with Nervana Graph. So what we've done is we've taken that sort of combinatorial explosion of backends that have to be written, and instead we've just created an intermediate representation that can be targeted by different connectors, and then the set of hardware transformers. So we've simplified the engineering effort many times. This is what the intermediate representation of the computational graph would look like. If you've seen data flow graphs from TensorFlow, this should look very familiar to you. So it consists of a data flow graph where, in this picture, we're representing sources by rectangles. So the orange represents internal data entering the system. And then trainable parameters are represented in gray. And then constants in the system are represented in blue here. So and this basically describes a sort of sigmoid nonlinear activation function for input, where we take external data and we take the dot product with a trainable set of weights. Then we add in a trainable set of bias vectors. Then we do numerical operations, negation, exponentiation, and adding a constant and taking the reciprocal. So this is what it looks like in the current Python front end. It's the same sort of idea, just in code. One thing that you'll notice is that we are passing into the functions axes. And these sort of allow for static type checking or static checking of different dimensions so that we don't end up compiling a graph that couldn't possibly run on the hardware. So Nervana Graph is just one more layer. If you're interested in running, say, a reinforcement learning algorithm and you want to run on a CPU, then on top of the CPU, you would probably be using an optimized library such as MKL. And then on top of that, a set of a library for doing tensor math. And then on top of that is Nervana Graph. And what this allows is for a user of different frameworks to basically optimize, to basically access this highly optimized backend. So this is the sort of scope of the current project now in the ecosystem. We are developing transformers for the Crest hardware, which I mentioned, CPU backends for training on Xeon CPUs, and GPU support. We're also targeting certain APIs exposed by libraries such as MXNet and TensorFlow. There's been a lot of other efforts that are coming up in this space. So Microsoft and Facebook have recently unveiled the ONNX format, which stands for Open Neural Network Exchange. And this is a way to sort of standardize models across different frameworks so that the different front ends can produce a computational graph that can be serialized and shared between different frameworks. We're currently working on expanding the Nervana Graph API to develop a sort of developer toolkit that would be accessible to developers of frameworks. And our system architect, Jason Knight, he's looking into other backends that are along the same idea of being able to run efficient code on different types of hardware, such as HALDI, PVM, and Weld. So who are the users of Nervana Graph? One of the main targets would be framework developers. So if you're a framework developer and you've developed a new framework that exposes some new novel API, basically you can plug into Nervana Graph and then be able to access a highly performant code path for your backend. It's also for developers of hardware and system software for new deep learning chips. So by targeting Nervana Graph as your instruction set, you can commit once and plug into a larger ecosystem. And then people who are interested in doing optimizations can basically do optimizations at the IR level and basically enable greater performance across a large variety of hardware backends. And if you are deploying large neural networks that have been developed in a different framework, you can basically target Nervana Graph and use that in your stack somewhere. And so you can export models from one framework and run it on other frameworks. So now I'd like to go over the instruction, the intermediate representation in a little more detail and talk a little bit more about the front-end connectors that we've developed. So if you go to the GitHub repo today, you'll see a collection of ops where basically we're trying to strike a balance. We don't want to have an op set that's too small, right? If it's too small, then we're not going to be able to basically express enough back-end primitives enabled in order to maintain performance. On the other hand, if we try to represent too many ops, then we can have this problem of op creep. So most of the ops are centered around tensor math, things like convolutions, general matrix multiplies. We have support for unary and binary element-wise kernels and things like folds and reductions. Another important thing that we have is tensor manipulation, slicing and broadcasting of tensors, reshaping, dim shuffles. And we have support in the graph for parallel ops and sequential ops. So basically, the ability to schedule computations to be performed in parallel. And then we have a support for assignment and to different memory buffers and other sorts of data mutation. Well, where we'd like to go with our IR set is basically to allow more control flow. So to allow for some sort of looping. And this can allow certain recurrent neural nets to be expressed more easily. The ability to iterate over selectable axes. And greater support for folds and maps. So we'd like to give users the ability to define their own subcomputations and be able to map that into structures of the graph. Our goal here is basically to enable people to avoid writing low-level assembly code or CUDA code and still get high performance and support for new recurrent kernels and layer types. I mentioned axes as being a sort of novel innovation of nGraph. So axes are basically a way to express tensor dimension management. So if you're working with a particular front end and you're writing a backend for that, it's basically a huge pain point because you have to follow the convention and be very aware of the convention that that front end uses. So that's a real pain point, and it is basically difficult if your backend device uses a different set of layout for the memory. So we use axes, which is just a way to give meaningful names to the dimensions of a tensors. It's completely optional for front ends that don't have this supported. And as I mentioned before, this allows the compiler to basically perform static verification. So you can tell that your computational graph will, in fact, you won't be having a tensor dimension mismatch at runtime. The current Python API exposes different functions to work with the graph. For instance, you can find all the variables that contribute to an op. You can do basic traversals and mutations. So here we're able to grab the lists of ops that contribute to another op. And then we have support for automatic differentiation. So given two ops in the graph, you can compute the derivative of one op with respect to another. So our connectors were originally called converters. And when we started writing, we basically had to take the low-level output of frameworks such as TensorFlow and Caffe and grab the protobuffer output of these, and then serialize it in, and then pattern match in order to create one or more nGraph ops. Of course, this was a real headache, so now that other frameworks are beginning to expose API access to them, we're leveraging that. So TensorFlow has XLA, which I said we're targeting, and as well we're using the API for MXNet. So how does this compare to ONNX, which is the Open Neural Network Exchange? So this is a new project that's announced by Microsoft and Facebook, and there's basically an open design, so you can go now and contribute your ideas. We are participating in this open design process. So at the moment, it just has support for inference, but it does allow a way to sort of serialize data flow graphs with an initial set of deep learning operators and to allow more sharing across different frameworks. So the main difference between a format like ONNX is that it's not connected to a whole compiler infrastructure. So there's no optimizers currently built in. And so that would be the main difference, I would say. So if you go today to the GitHub repo, you'll find the Python API, the implementation. You'll have access to the Neon front end, and through that you're able to run multi-layer perceptrons, convolutional nets, recurrent nets, GANs. There's support for serialization, and if you use TensorFlow, you may have come across TensorBoard. So this is a very cool project that allows you to visualize and sort of expand and collapse your TensorFlow network. And so we have support for this in nGraph. And then we have our TensorFlow XLA connector proof of concept. The core nGraph team is currently working on porting the set of ops to a C++ API. And we're basically switching to C and C++ to get better refactorability and type checking. And performance, of course. We're working on developing a full TensorFlow XLA backend and integration with MXNet. And we have plans to release external op or FFI support, which will allow you to write custom user kernels, basically inline. All right, and now I'd like to talk about the backends. So the graph transformation architecture, you may have noticed, sounds very similar to the LLVM project. And that's no accident. It wasn't, in fact, inspired by LLVM. So what we do with the intermediate representation is this is our sort of core set of ops that we're going to transform to do the abstract tensor operations. And then we're compiling down to an executable primitive. So some example passes that you might see in the optimizations would be things like arithmetic simplification, taking, for instance, removing redundant ops. If you have a variable and you take the exponent and then you take the logarithm, that of course can be simplified to just that variable. In the optimizations, we're also doing things like pruning redundant dimensions, doing element layout. At this stage, we're able to do things like storage planning and start to think about how memory might be laid out on the back end. And at this stage, we're able to sort of look into what parallelism opportunities might be inherent in the computational graph. So you might be asking, why don't we use some existing compilers such as LLVM or ICC? So I would say that deep learning is inherently different than doing normal numerical computing in that our operations are primarily based on tensors. So these other tools don't really offer the right set of abstractions that we want. So tensors are just another word for large multidimensional arrays. And deep learning tensors are fairly regular at this level. And there are many optimizations that we want to be thinking about at the tensor level. So we do tricks like horizontal fusion in order to simplify the amount of computation that needs to be done. When we think about memory liveness, we need to think in terms of keeping tensors in memory instead of registers. And by designing a system on top of these compilers, we're basically still able to reuse the code gen of those in the transformers. So our proof of concept for a C++ code gen is leveraging the just-in-time compilation that is existing in LLVM. So then, why would we develop this, and why wouldn't you just program directly in CUDA or cuDNN, which is a set of primitives for deep neural networks, or using something like MKLDNN if you're executing on the CPU? Well, if you've ever looked at these, they basically offer a very low level of abstraction. It's not something that you want to be programming in. You're basically confronted with a lot of raw matrix multiplications and convolutions. You're sort of at the memory management level of buffers. If you're a data scientist, you definitely don't want to use this level of control when you're just trying to write a model. And there's many ways that you can hurt performance if you really don't know what you're doing when you're working at this level. You can easily get memory layout wrong. That's wrong for your device. The allocation may not be optimal. And doing things like operation fusion is very hard to do. So why would you be interested in looking at Neon versus, say, other popular and frameworks such as TensorFlow, PyTorch, or Caffe? Well, these are all very good frameworks, like if you're running a production model, TensorFlow is a very popular choice. PyTorch is very popular among researchers. Caffe for computational vision people. Well, we designed Neon to basically set the bar for performance. So Neon contains a set of highly optimized GPU kernels, which basically set records for GPU performance. Neon is a framework that's designed more for applied data science. So when we have our data scientists do projects for customers, they're all developing and contributing to Neon. And by having another framework, we're able to sort of use it as a laboratory for deep learning infrastructure. So Neon is where things like axes originated. We have notions of containers, where we're able to take layers and add them to a container in order to construct more complicated networks. And we have support for dynamical networks. Another thing that we can do at the backend level is start to think about distributed processes. So we have a distributed process transformer, which is called heater. And the heater transformer works by taking a computational graph and inspecting it and following the edges. And the user will basically have specified in their script that they'd like to take this part and distribute it across different machines. And so then we're able to clone the graph and create subgraphs, which we call heater subgraphs, and split those and create communication nodes. So currently we're working on adding heater support for MPI. And what this means is that the user will basically have to modify their script in order to add some MPI-aware the places where the heater should basically distribute that using MPI. So at the moment, we have this set of transformers. We have a GPU transformer, which is using the Nervana GPU kernels, which executes on CUDA. Then we are working on CPU transformers using MKLDNN, and we have a reference NumPy. We have the heater transformer and transformers for Lakecrest. The common optimizations that we've implemented are operator fusion, pattern matching utilities, memory sharing, and layout. So the roadmap of things that we'd like to accomplish at the rest of 2017 is basically a seamless interop with TensorFlow through the XLA, a multi-device training support via heterogeneous transformers. We're working on then allowing multi-node training for data centers. And we have a set of performance milestones where we try to achieve the highest performance for a reference set of modern neural networks. The team is also working on developing MXNet transformers, additional front ends, CNTK, and a PyTorch front end. We'd like to see more backends, of course, connect to all this as new novel deep learning hardware is developed and brought to market. And we'd also like to focus on deployment operations. So as deep learning is seeing more sort of edge devices, things like weight quantization, where you switch to a lower precision format, is something that could be built into nGraph. And weight pruning, which basically squeezes the amount of the memory required for neural nets to allow them to execute. I'd just like to take any questions at this point. I finished a little bit early, so if anyone has any questions, I'd be happy to answer. Yes? You had a question? Yes?
What's the relationship between nGraph and Big DL? Is there one?
Big DL? So Remind me of Big D. That's a cloud-based solution.
No, I believe it's a big data distributed deep learning connector for Apache Spark built by the Nervana Graph.
I don't think we have any. I'm not familiar specifically with Big DL. So we have a cloud system which will basically allows data scientists to upload their model to a cloud, and then we sort of take care of executing it in the data center. Yes? So our paper describing the format is coming out at NIPS in December. We also have Nervana Con, which is taking place at the same time in December. So the hardware is designed for training, right? Yes.
Are you tied to MKL or will it work for any class library on the backend?
At the moment, MKLDNN is its own repository, so it's not tied to MKL, I believe, at the moment. It's sort of working on top of lower-level BLAST primitives. So I don't recall having to install MKL in order to run MKLDNN. Okay, if anyone else has any other questions, I'll be available in the back. So I want to thank you all. Thank you.